In the run-up to Christmas, I put a little public service announcement video out mentioning that a local DIY retailer had issued a recall on some of its plugs, its remote control sockets. And I decided at that point that, since eBay doesn't actually have standards, let's go on eBay and find the shittiest remote control socket we can find. And this is theoretically, I say theoretically because it's not that shitty at all. It's infrared for a start, which makes it kind of shitty, but not completely shitty, because it means it's quite close range and it's not going to be affected by external influences. It's also quite clever in the fact it doesn't come with a remote controller. You supply that yourself and it uses any standard controller. And I'm guessing these ones use the standard code format RC5, but I could be wrong. So this is described as new AC 220 volt, noting that it is for the Chinese market with their Chinese bipin arrangement, which looks a lot like the American bipin sockets. But 220 volt, 500 watt wireless IR remote controller power socket outlet switch. And it cost, the name is very good, Deal Dear. It cost £2.65, which is nothing, £2.65 inclusive of shipping. And the first thing I noticed about this, it's got an earth pin here, but the input has no earth pin. So although they've got all the metal behind the earth pin position here, it's completely functionless. They also have a position for sticking plugs in the side here of the little bipin plugs like these, which is interesting enough. And of course, it lets you jam just about everything else in, which, talking of which, let's jam something in. Let's jam in a piece of flickery mains voltage LED tape, but let's bring the hoppy in first and do a slight analysis on it. So we plug it into the hoppy meter. And the first thing we notice is it's drawing 36 milliamps. Now you think at 36 milliamps that sounds a lot, particularly at 244 volts, which it is at the moment. But in reality, because it's using presumably a capacitive dropper, the power is only 0.85 watts. So let's see, it's drawing that at the moment. If I push the button to turn it on, 0.8, it's 0.85-ish. It drops slightly, so it draws slightly less power when it's off than when it's on. That does suggest, along with the absolutely appalling power factor of 0.096, that's quite awesome actually, awesomely bad. But that's just because it is using the capacitive dropper and it suggests that it's using a low voltage rail inside with the modest current of 36 milliamps. So when I plug this into it, what you can do is you can turn it on and off with the button on the unit. But if you want to program a code in, grab any remote at all and turn it on and then hold this button down until it comes back on again. Then it will start flashing. Point the remote controller at it, push the button of your choice. In this case, I pushed the power button, which seemed logical enough, and it programs it in. Here's another remote control. It's a different code because I'm pushing the power button, pushing all the buttons. Nothing is happening. So I want to program this one as well. Turn it on, hold down the button, and after a short delay, it will come back on again. Release, the button is flashing, power again, and now I can control it from either this remote control or this remote control. So you can program it, and I actually tested this and decided, since you can program it, you could, say for instance, watch this. If I turn it on again and I put it into the programming mode by holding it down until it comes back on, and then I hold down the green button, you can actually then, it's remembered that code as well, so it now responds to on, it responds to green, and it responds to this button as well. Noting, incidentally, that it is quite directional. This is quite good in a way. It means you can selectively point at the unit from a modest distance and trigger it. And I decided how many codes can it, how many codes can it store. So to test that, I used this remote last night and I just put it into program mode and pressed each one, then put it in program mode, pressed the next one, and I worked my way down and just worked my way right down to the bottom. By the time I got to the bottom, it had forgotten the top ones. And when I counted them up, the 15 bottom ones worked and this one worked, which means it stores 16 codes before they start falling off the edge, so to speak, and getting forgotten. That's quite good. That's quite impressive. I also tried it with a TV remote control and it just completely ignored it. It would not recognise that at all. Oh, next feature, since there are no instructions, do you know, it says on the internet, it says, hold the button for 3 seconds, 1, 2, 3. That's it in programming mode. Is it hell? It's not in programming mode. It's still just going to go on and off like that. It's not going to remember any codes. There are 2 modes you can use with it. The first one is to program a new code where you start with the power on. There's a little red LED here that indicates that. If you want to delete all the codes, which is the second mode, start with the power off, hold the button on, down, and the power comes on initially, and then after a while it'll go off. Modest while it'll go off, and now it's forgotten all the codes. So you've deleted all the codes in it, and you can then reprogram it as desired. It's not bad, it's quite clever. Let's take it to bits. And before I take it to bits, let's have a guess at what's inside. So the first thing that surprises me here is I was not expecting there to be a relay. The clicking relay was unexpected because it didn't seem like there's much room in here, but it does look like it's space optimized. So I'm guessing there's going to be a relay either under here or under here, just hugging that sort of middle pretend earth pin. So I'm guessing it's going to be based on the classic 8-pin ubiquitous random microcontroller with no numbers on it. So the input is going to be AC, and since I'm not even going to mark live and neutral because it can go around either way here. And let's say load. And there's going to be a switch contact to the load. And then, of course, you're going to have the 2 output pins and the socket for that. So there's the 2 AC pins going in. I'm expecting a capacitive dropper. It's the only logical way to do it. Resistor would be terribly wasteful at 1 watt power. It's actually going to get quite hot as it is. 35 milliamps would be quite a... what would that be, actually? Let's work that out. What would it be if it was actually drawing... That was roughly about 244 volts at the moment, times 0.035. If it was like measuring, if it was actually using that current, it would be drawing about 8.5 watts. That would be toasty hot, but it's not. It's using the capacitive dropper, which basically has the voltage and current waveforms out of sync by the voltage required. So it just creates this... It's very hard to describe, but it's a very efficient way of dropping power since there's no heat from the capacitor. So that will have a resistor across it, a discharge resistor, to stop you getting a zing off the pins. Then it'll be going into a bridge rectifier. This looks like the classic circuitry so far, but the bridge rectifier may not be what you'd expect. The bridge rectifier may actually have a couple of Zener diodes as forming in place of 2 of the diodes. And if they used, typically in these things, they'll use a 24 volt supply because running the relay at 24 volts means it can operate at much lower current than a 12 volt relay. And it keeps things simpler. If they had a mains voltage relay, that would involve super fine windings. It's quite a complex thing. And also it would involve mains switching circuitry. So it just makes sense to have 24 volts. So there's a couple of ways to achieve that. Here's the 24 volt rail. And they can either cap that within the bridge rectifier. They can effectively use a couple of Zeners in series instead of normal diodes. And they both rectify and also cap the voltage. And if they're 12 volts each, that would create a 24 volt supply. The other option is to have a smoking hot diode, and it usually is quite hot. Keep in mind, this is dissipating 24 volts, 1 watt roughly, almost 1 watt when it's off. So that is going to be a very hot Zener. Let me draw the smoke and sort of heat coming off it. Another option, which I very much doubt they're using here. There'll be a smoothing capacitor here, probably a coupling capacitor in here. Let's draw the wee bits in that you'd expect. Another option is some of them have a very clever multiple transistor system whereby if the relay is on, it's sort of clamping the current limited supply down from this capacitor to the point that, you know, it's 24 volts across the relay. But if the relay is off, it switches in a resistor instead, and that has roughly the same impedance as the relay, and it clamps it down to about 24 volts too. Guess at the value of that? 470 nanofarad is my guess. 400 volt, hopefully. The next thing we need is a 5 volt rail for the logic. 5 volt. That could be a resistor to limit the current from there, and then a little Zener diode to cap that to round about 5 volts. 5 volts are right next to that. Value capacitor, wild guess, 100 microfarad. Probably wrong. 25, say 35 volt to allow margin. That might be 100 nano, but it will probably a surface mount component, wouldn't know. That'll be quite a high value of resistor because it's just providing enough current for this circuitry to operate. And what we're going to have here, we're going to have the microcontroller, CPU, and it's going to be connect on that 5-volt rail. It's going to have a resistor and an LED. That's a little red LED there. The red LED could have been connected across the same output for the coil, but during programming mode, that red LED flashes independently of the coil, so it does have its own independent output. So let's give it its own independent output. There will also be an infrared receiver, let's call it IR, which will have a 5-volt feed, 0 volt, and then the output from going to the CPU, and that's actually hidden under here. It looks like a fairly standard component under this little red window. And the other thing, it will have a button, which will probably have its own, either an external pull-up resistor or internal. That's this button here. And then the output will go through a resistor. This is all wild guesses. The coil from the relay will come down to that transistor. This is all wild guesses. And there may be a diode in reverse parallel to the coil to snub any spike and protect the transistor. And that is what I'd expect to find inside this unit, but I've not opened it up yet. So the only way to find that out is to open it up. Let's open it up. So we've got a little warranty label here. Ooh, we've got a QC Pass sticker here, and they've put labels over the back here as well. They're all about to bite the dust because, well, it's a cheapie. We're not really bothered about warranty or that. I think there's a screw under here. It could be wrong. Yes, there's a screw under there. Oh, these stickers are actually stop it from opening. Let's slit them. Oh. Rightio, that's an interesting arrangement here. Why is that not easily coming out? The pins are going in, and there are soldered connections. How does this come out? Is there something I'm missing here? Am I going to have to use... Oh, brute force and ignorance did win. So here's the completely useless. Let's nudge down in this. Here's the completely useless earth connection that does nothing. Oh, that's messy. The spring contacts literally are wedging. When you plug something in, it goes between this contact here and the plastic housing, and they've just got a splodged across onto that. There's the relay, which was exactly where I predicted. It's actually down here. Noting in the front it says E, L, and Earth. That should be, I'm guessing, is it another country? E, we'd normally have that N, but that would be L. That's very odd. And here is the circuitry, and this is what's really interesting. Am I going to be able to get this out? Yes, I am, if I use a bit of unreasonable force here. Right, what do we have? Oh, blimey. Rightio. Here's the infrared receiver. There's the capacitive dropper. There's the bridge rectifier. There's the external zener, a big one, really big zener. That's going to get pretty hot. There's the capacitor. Is this bright enough? Am I going to completely ruin it by opening this exposure and just going like, that's better? I had to have that exposure set down lower a wee bit earlier because the white cases always just flare out. It's quite a wide contrast here. The capacitor, I guessed 470 nanofarad. The value is 470 nanofarad, 400 volts. Whether it actually is that is debatable. The bridge rectifier is just based on 4 discrete diodes here. The zener is quite chunky. The electrolytic I guessed at 35 volts and what was it, 100 microfarad? 220 microfarad, 35 volts. Good enough, he lied. The relay has a transistor locally, and it's got the reverse EMF diode, and it's got the resistor there. What it's got here, though, this is surprising. This is not what I was expecting. This is probably the microcontroller, and this is probably a memory chip. I always expect it to all be integrated into one. Let's see if I can get close. Atmel 24CO2N. That's a standard serial memory chip. The microcontroller doesn't have anything written on it, but it's got so many pins. Why did they use that specific microcontroller? Whereas I guess they might use a power supply. Is this a little 5-volt regulator, 78L05? 78L05. Hold on, let's get a different magnifying glass. Let's let you. 78L05. It's going to be at focus at some point. So that is a discrete 5-volt regulator. That's when I was wrong. I thought it might be a resistor and zener. They've used a separate regulator and they've used a small smoothing capacitor for that. This resistor here might be a pull-up or pull-down resistor. Not so sure about that. 33 ohms. Not sure about that. What that's for. I wouldn't expect that to be in series with the resistor. 10310K, I would expect that, but that could also be a pull-up or pull-down resistor for the infrared sensor, which has a little less decoupling capacitor right next to it as well. It's all fairly textbook, but you know what? It's better than I was expecting. That's quite extraordinary. You know, it's in a shitty casing, but you know, if you whipped all this circuitry out, I'm going to get the thermal imaging camera on here and I'm going to plug this in and we'll plug this into the power. This is where things get a bit spicy for me. And we'll see how hot the Zener diode gets. So I'm going to bring in a adapter. I'm going to kind of gingerly shove this in here. Then I'm going to cautiously make sure I've not got my fingers near anything. And then I'm going to plug it into the mains. Right, that's now operational. Can test that by clicking that button. This is where it gets extremely precarious because I can't really hold the circuit board in any way. Okay, right, okay. Right, the circuit board is rigid enough in wires that I can poke it. It will be slightly out of focus because it's at a different height. Right. So that thermal imaging camera on. Let's let it boot up. The thermal imaging camera is based on a processor, so it will take a while to boot up. I'm just going to zoom out here, and we'll see how hot that Zener gets, because that is the one that's going to get the hottest. Second hottest component will be this little voltage regulator here. So it's booting up. Then I'll focus onto this once it's all booted up and ready to go. It's thinking about it. Oh yeah. It's not that bad in relative terms. I'm going to have to use the. I'm going to have to get the change the mode in this. Measurement. No, it's not the measurement. I want picture in picture. I want the image mode, should I say. I want that to change that to just thermal. That gets rid because I'm at fairly close range. It's not actually too bad. It's not getting overly hot. That's not getting too hot at all. That component there is reaching about, it's been on for a modest length of time, it's reaching about 30 degrees Celsius. Hold on, I'll show you this. Let's focus down on to this. Is this all going to work, or is it going to be horribly wrong? So we've got a little bit of heat over, just watch what I touch here, there, which is showing approximately, that's the voltage regulator, which is showing about 27 degrees, which is fine. And the Zener is showing about 25 degrees, which seems too low actually. Am I obscuring something here? No, that really is. It's not running very hot at all. Oh, the relay is on. That's possibly why it's clamping the voltage down. Right, okay. Now that's going to get hotter. Yes, that is getting hotter now. We can watch the temperature rise in that. Yeah, now the relay is off. The temperature on that Zener, the voltage has shot up. And it's rapidly rising. It's now up to 60 degrees Celsius. 65. 66. It's going to get pretty hot, but this is really common in these power supplies. Effectively, the zener, when the relay is off, the zener is basically shunting the supply down, and the supply has to be able to supply enough current for that relay. So it's all going into that tiny little component in there, and that is getting very hot. Quite often, even in professional equipment, they'll have sort of like brown marks around them in the circuit board. It's currently at 76, 77. It's continuing to rise. So all in all, while this is continuing to heat up, the biggest surprise in this were that they weren't just using a standard little 8-pin chip with the built-in memory. They've used the external memory chip, and they've used a larger microcontroller. They've used a capacitive dropper, a very stereotypical capacitive dropper. Textbook circuitry. Really impressed that they've used the voltage regulator, a proper infrared receiver with the decoding built in, which is a standard thing, and its own fairly smooth separate power supply with its own little decoupling smoothing capacitor there. What value is that? Being cautious that I don't want to drop live things on myself here. The value of that capacitor is very small indeed. Where's my magnifier? I'll guess 100 megafarad for this one, maybe. It's got a big splash of solder on the side of it, which doesn't really help much. That one is... can't read it. I'll leave a note down below, because it's not very... I have a nasty feeling that the bit that's got a big splash of solder on it might actually be the bit that the value is written on. No, I'm talking shit. It's 100 megafarad, 16 volt. Oh well, I got that one right. So let's see how this is going now. I've left it a while to heat up. Oh fuck, I'm really close to that mains connection. It's about to go bang, I think. It's stabilised at about 85 degrees. That's pretty hot, but it'll get even hotter in a higher ambient temperature. So I'd allow for up to about 100 degrees in there. Oh, yeah, see, now I've got live circuit board next to live pins sticking out, and I have to just gingerly just hoik everything out. There we go. So, you know, for what it is, the circuitry is really impressive in there. The zener's getting hot, but you know, who cares? That's what often happens in your average microwave oven clock. You'll get a hot zener running in the background, clamping the voltage down. It's, you know, for something so cheap, I don't like the housing much, but for something so cheap, it's almost worth it just for this little module for putting it in your own case or something like that, and make your own completely non-compliant infrared remote control switch. I really like the fact that it can store 16 codes from a standard remote. That is quite smart. But there you go. Big surprise. For such a shitty little thing, it's actually quite nice inside. I should also mention that hot zener is also mounted vertically and well away from the other components. So it's not that bad at all.